In other words, these thermodynamic models are trying to describe the equilibrium compositions of the vapor and liquid phases as you change temperature. All right, so equilibrium composition between gas and liquid phases can be estimated by thermodynamic tools. Right? And so let's actually start discussing what those tools are. All right, so the first one I'll introduce is actually one you've already seen before. And so in general, whenever we talk about gases or vapors, one important property of them is the pressure, right? That energy density we mentioned in all the way back in chapter 5. All right, and so if you have a multi-component system, the total pressure in the gas or the vapor phase is going to be the sum of the partial pressures, right? And so if you remember from the previous videos, this was Dalton's law, all right? So I said this was an important equation, and that you'll see it again, and here it is. You're seeing it again. All right, and so just to, at least let's apply Dalton's law, let's consider the case that we have two components in our system. What Dalton's law would describe is that the total pressure of the system is going to be equal to the partial pressure of the A species plus the partial pressure of the B species. That's it. That's all it's saying. All right, and so that's what Dalton's law is telling us. Another very important thermodynamic tool that we're going to come back to quite often in this course is Raoult's law. And so I mentioned here, in Dalton's law, that total pressure is equal to the partial pressure in the vapor phase. So I'm specifically talking about the vapor phase here. Okay? What Raoult's law allows us to do is it allows us to relate the partial pressure of one species in the vapor phase to the partial pressure of a species as it's coming from the liquid. All right? And so to write that out mathematically, what Raoult's law tells us is that Pi, our partial pressure, Pi, is going to be related to the total pressure of our vapor phase via the mole fraction of that species. All right? And so what I mean by that is that Pi is going to be equal to Yi times P, where this is mole fraction in vapor. Okay? That's the first thing Raoult's law tells us. And so this portion of the equation is only referring to, the mole fraction of the species in the vapor phase. Okay? Now the second part of Raoult's law, what it tells us, is that this partial pressure, this Pi, which is equal to Yi times the total pressure in the vapor phase, that's going to be equal, or that's going to be related to the partial pressure of that same species in the liquid phase via this relationship, Xi times Pi star at some t. All right? And so just to emphasize this side of the equation, YIP, is talking about the vapor phase here, while the right-hand side, Xi Pi star, is talking about the liquid phase here. Okay? Now, as far as where we get Pi star from, if you remember in the previous videos, Pi star we could get from Antoine's equation. All right? And so all these things are starting to come together. All right? And so really, just to kind of summarize what Raoult's law is describing, basically Raoult's law gives us a tool that allows us to relate the composition of the vapor phase to the composition of the liquid phase in our system. All right? And so, this is a very powerful tool, and you'll see later how this will allow us not only to calculate just mole fractions, but it will allow us to actually calculate entire phase diagrams for multi-component systems. All right? But of course, like any sort of thermodynamic model, it is based on a few assumptions. Right? I won't go through the actual derivation of Raoult's law. You'll see that later in your thermodynamics courses. But I will tell you that Raoult's law works well if the liquid mole fraction of the species is close to 1. Right? So, for example, liquid water in equilibrium with air. For this sort of system, Raoult's law is appropriate to use. Okay?